Hi, I'm John.
And I'm Michael.
We're going to demonstrate resonance of sound waves by playing a tone into a water-filled tube.
Waves are a form of energy, and when waves encounter other waves, we call that interference.
There are two types of interference, constructive and destructive.
When waves interfere constructively, the apparent strength of these waves increases. If they interfere destructively, they can decrease in strength or even cancel out.
Since sound is a wave, an easy way to experience this is to play a tone or sound wave into a tube filled with water.
The surface of the water acts as a reflector for the sound wave, effectively making a second, reflective wave that interferes with the wave coming directly from the source, in this case the speaker.
Under the right circumstances, constructive and destructive interference will produce a standing wave in the tube, making the sound resonate.
Let's observe this by playing a tone of 800 Hz from the speaker into a tube in which the water level is constantly getting lower. Pay attention, as when we hear these resonances, I will mark them with these elastic bands. Notice that we heard resonance occur twice throughout the tube. Our first resonance occurred at this top elastic band, and our second resonance occurred at the second elastic band. As John mentioned earlier, when we have resonance in the tube, we'll have a standing wave. This means that the first standing wave occurred at the top elastic band, about 1/4 wavelength down the tube, and our second resonance occurred about 3/4 of the wavelength down the tube. This means that there is a difference of 1/2 wavelength between these two parts in the tube. Thus, these two elastic bands should also have 1/2 wavelength in distance apart from each other.
We also know that the velocity of a wave is equal to the frequency times the wavelength. Knowing that the velocity of sound in air at this temperature is 343 meters per second, and that our frequency was 800 hertz, we can calculate our wavelength. And our wavelength should equal 43 centimeters. 43 centimeters. And our wavelength divided by 2 is 21.5 centimeters. Now, Michael, what is the reading between those two elastic bands?
21.5 centimeters.
As we would expect. Thank you for watching our Penguins video on the resonance tube.